Okay, so today we're gonna. I plan to discuss these two topics, but maybe I'll just discuss radial quantization. And this is a pretty big topic in itself. There are lots of details to work out. So maybe we won't have time to discuss the operator state correspondence today. So, and the motivation for the radial quantization and the operator state correspondence is it all leads to the operator product expansion, which is a tool in any quantum field theory, but for conformal field theories, this operator product expansion has some nice features that are unique to CFTs, and it's the main working tool, computational tool to do conformal bootstrap or things like that to solve a CFT. Okay, an interacting CFT, which is in principle not trivial at all. So in order to get to the operator product expansion in CFTs, we need to discuss radial quantization, then the operator state correspondence, and so on. This will take maybe 2.5 lectures. Okay, and the motivation for it all starts with the 2, 3, 4 point functions that we computed last lecture. And just to remind you, I wrote them out here. And the important features is that the 2 point functions are completely fixed by conformal symmetry. The 3 point functions, they have the functional form completely fixed, but this structure constant C, I, J, K, another term by conformal symmetry alone. And similarly, when you go to 4 point functions, you can only factor out some the scaling behavior here that you can do in more than one possible way, but you still have this conformal block f of u and v that is an arbitrary function of these two variables, and u and v are the conformal invariants that we discussed last lecture. So what happens is 2 point functions are completely fixed by conformal symmetry. Remember, we normalized the concept to 1. 3 point functions are fixed up to these structure constants, and the 4 point functions don't even know the functional form in principle. Okay, to determine both the structure constants and the conformal blocks, we need the dynamic information that we get eventually by working out the OPE, okay, the operator product expansion. And just a quick computation. I did not do last lecture. I just gave you the result. The number of just like a remark. The number of conformal invariants that can be made from 2 endpoints. Number of conformal invariants given endpoints. I told you that it is n times n minus 3 over 2. And one possible way to count this number is, remember how we computed the 4 point function, because say if we have n points, actually there is a way. Let's do it this way. We have n points. Okay. And you want a pair, then 2 by 2. Okay? So you pick 1 point, then you have n minus 1 points. Okay? But remember, by Poincaré invariance, it shouldn't matter the order, just the modes of the difference. So it doesn't matter the order, so we divide this by 2. Okay? Now from these points, we can determine exactly we have n constraints coming from conformal invariants. Similar than what we did in the computation of the 4 point function last lecture. So when you compute this, you get like this. You get n squared over 2 minus n over 2 minus n, and this you get 2 here minus 3. Then you get the other ways, maybe more physical ways, playing symmetries. I guess it's the faster one. Okay, so let's move on to radial quantization itself to eventually in a few lectures get to determine, see how to determine these guys and work out some examples finally. Okay. Okay, the radial quantization starts with the discussion of some representations. Of fields. Conformal representations of fields. Okay? And the way to do this, we use a trick that we learn on when studying the Poincaré group, in Poincaré representations. We look for representation on fields located at the origin. Having worked out the representation at the origin, you just apply the translation and find the representation at any other point in space-time. Okay? This is the story of the little group and so on. Okay? So, recall we had translations. We had rotations that also include Lorentz transformation and boost. We have Minkowski space-time. We have the scalings. And we have the special conformal transformations. Okay, we have to find the representation of fields of all these transformations. And we will look first at fields located at the origin. So, translations don't matter much, again, because we fix at one point. So, we'll start from this. We'll start from rotations, and we'll say that rotations acting on a field phi can be any field of any representation. It could be not necessarily a scalar. It could be a vector, a tensor, a spinor, and just omitting all the indexes. Okay? And I'll say this is will be a spin matrix in general. If it is a scalar, it just vanishes. Okay? There is no orbital again because it's located at the origin. No orbital angular momentum. The scaling operator acts on the field located at the origin. I'll call it delta tilde, and the reason for the tilde will become clear in a few moments. And then finally the special conformal transformation will give I'll call it a kappa nu acting on the field. Okay? These are on the left-hand side we have the differential operators that represent the symmetries. Okay, we could also work this out with the Hilbert space operators, in which case we'd have to use commutators here. But it's we're just working out with the differential operators that represent the Hilbert space operators. So there won't be any commutators here. Okay. Now, what we actually have to do is determine these guys. Okay. This will be the representation.
Why did sorry, I didn't understand. Why didn't you use the translation?
Translation? Because I'm fixed at the origin. So okay. Actually, if you want, it is just p mu equals some p mu. You don't know what it is. Suppose you don't know what it is. It will be just minus I partial. Okay. But it won't matter at this point. Okay, only when you translate.
But when you fix the origin, it's like we're choosing a gauge or something like that.
No, it's a freedom we have when you quantize any theory. Okay, I could choose 2, 3, pi, anything. Okay. The orange just is a special conformal symmetry. Maybe the name radial in radial quantization gives it away. You're gonna understand this. But this is a trick that is when you study the Poincaré group. Remember, you conclude that instead of looking to the representation of the entire Parte group, you can simplify your job just by finding the representations on the little group. Okay, you choose you fix some momenta, some reference momenta, and then you find the representations acting on this momenta, and then you just can apply Lorentz transformations to construct the representations for any other momenta. And then you just separate some case like, okay, this has k squared 0, k squared positive, negative, and so on. So it is a similar story here. I'm just fixing the origin. I'm going to find the representation of the origin. Then I'm going to translate this field and find the representation at any point x. Okay? This is the induced representations. Induced because we're going to find the representations at the origin and induce representation at any point x by translating these fields. Okay? It's just a strategy. And again, we have to find sigma mu, delta tilde, and kappa mu. And if they are indeed representations, they must obey the conformal algebra. Okay? Then, so don't get anything wrong here. This means that if they are they furnish representation. Then this implies that okay, this is just one piece of the conformal algebra, okay? I'm just not writing up the commutators that involve the momentum because we're not looking at the momentum here, okay? So if these guys do furnish a representation, they must obey this algebra, okay? Now here comes the important observation. That the scaling operator here commutes with the rotation operator. So you have Schul's lemma, it's a result in representation theory in algebra and mathematics. That's basically, it says that if these guys do commute with the rotation operator, then delta tilde must be proportional to the identity. Okay? It is actually a number, delta tilde, times the identity. Okay? This is one of Schur's lemmas. Okay? I guess there are two of them. So, if this guy is actually proportional to the identity, then if this one, as the first consequence this has is when you look down to this commutator, if delta tilde is the identity, then this commutator vanishes. So kappa mu itself must vanish, okay, by consistency. So kappa mu is actually 0 as a consequence. Okay. So we already determined that the job in principle is actually over. We determined that k must be 0. Okay. Delta tilde must be the identity, some number times the identity. And these guys, again, if you're sitting on the origin, there is no orthogonal momentum. So this matrix must be spin matrices. Okay, if it is scalar, it just vanishes. If it is fermions, it will be a commutator of gamma matrices and so on. Okay, but there is still one more thing that we can say about delta tilde. It is again a result from mathematics that says the following: scalings are not bounded transformations. Okay. And so there is a result in representation theory that unbounded transformations, they must necessarily be represented by non-unitary operators. Okay, and as a consequence, their generators won't be Hermitian, and as a consequence of this, their eigenvalues will have to be very imaginary. So the result is this. Okay, delta tilde, I'll just call it like minus I delta with delta a real number in principle. Okay? Are there any questions about this? I mean, I just use pull out the pocket two mathematical theorems. I mean, Schur's lemma is pretty much familiar. This might be a bit less so.
But this already appeared when we look at the commutator stories.
Yeah, we can already suspect this by the commutator because it is, you have the algebra, but there is a factor of y sitting there. Okay, and now we understand. Okay, looking at the representations of fields and the mathematical reasoning is exactly this. The same thing happens in the Poincare group for the boosts. The boosts are not a bounded transformation. Okay, you can get as close as you want to the speed of light. Okay, so it is an unbounded operator, and you look to the generators, you see they are not Hermitian.
I like in your second argument, I still didn't get, you said it's none, so it's not in unitary, so the generators are not necessarily Hermitian, but this means it could be a general complex number. So why does it have to be imaginary?
I don't know how to prove this.
But there's something more than not being. So it has to be actually anti-Hermitian or what?
It must be purely imaginary.
Yeah, purely imaginary. So
I mean, it is not the only instance where the eigenvalue can be. You can have purely imaginary eigenvalues in other situations. Yeah. But in this situation, is one of those situations that you can have purely imaginary eigenvalues. It's just I don't know how to put this. It's just a result on mathematics, and you just write it unbounded scalings. Okay, these are the points. Scalings are unbounded transformations. Now this implies that they are represented by non-unitary operators. I think that is what the theory is about. And as a consequence of not being unitary, the generators, the D itself, this D won't be Hermitian. Okay? And then it will have a pure imaginary eigenvalue. Okay. I don't know if there is any other way to prove this. I mean, as I said, we can already suspect something like this by looking at the algebra because there's a factor of I sitting there. But the actual way to prove it is this theory that says that this. Okay. Any more questions on this? If we can accept this, our job at finding the representations at the origin is over, and then we must apply translation to find the representations anywhere else in space-time. No questions? Okay, so just to repeat here. So what I found it is the rotations acting in the origin gives just spin matrices. The dilatations they give a perimetric eigenvalue, and the conformal transformation just annihilate the field. Okay, u0 because kappa mu was 0 as a consequence of delta being identity. Okay. Now we must actually do find the induced representation by applying translations. Okay. So. Which is applied by this operator. Okay. X here is actually I'm gonna put A because X gives you the impression that this variable is just it is a fixed position vector. Okay. I'll apply translations, meaning like this using this operator for the representations. Anywhere else. Okay. So just we're gonna remember that these fields, if you have a field sitting at the origin, the way to apply transformation to it is to apply by similarity transformation. Okay, because to translate a state, we just apply an exponential, then fuse, operator, and so on, transform correspondingly by a similarity transformation like that. Okay, so this is exactly what we're gonna do. We're gonna take, say, the second equation. We're going to multiply, just so I get all the minus factors correctly. Just check. Defining like that. Okay, that's it. Okay, I'm gonna multiply on the left by this explanation. I'm gonna multiply on the right by this exponential. Okay. So I'm going to have since it's a number, I can just take this exponential and bring it up here. Okay, this is already the field point A. Okay, but here we still quite not. We need an exponential here, and this exponential, of course, it doesn't commute with the scaling operator because of the momentum operator here, momentum generator. So we just come here multiply. Okay, by this factor. Okay, so this guy here will give the field located at point A. We're going to end up with this. Okay. So we have to compute this. You can just use a household formula, or you can just simply expand this exponential and keep the first order. So you just got identity minus a mu acting on d, and from the expansion on the right hand exponential, you just get plus I a mu d mu. Right, next. Okay, everyone follow this step? So that is just the reason why I wrote a instead of x, because it is a constant vector, okay? So the momentum won't differentiate this guy, okay? Just a constant. What appears here then is just the commutator, okay? We have the identity acting on d with d. Okay? So we have this d. This is acting on the field at point A, and here we're going to have mu. If I factor out minus I, in mu we have the commutator of d actually. Okay. And now this guy gives minus I mu, okay? Now, what I wrote d mu gives plus I mu, so it is the Radial operator, okay? I have a mu d, so it is minus I. Then in the end, just working this out. I will exchange now a for x. We end up this guy sitting here, this guy you bring over to the other side. You factor this a minus y I there. We end up with this. Okay? And I explicitly use the moment operator as represented by minus I partial mu. Okay? Any questions about this? No? Okay, so we just repeat this game for the special component transformation in the rotation if you want. Rotations, of course, we just, I'm not going to do it, just write the result. We all know what it is. It is just still the spin part. And we now acquire a plus or minus. We acquire some ortho momentum. Okay? For the special component transformation, it is just a bit longer computation because you must play this game, but when you get the commutator here, the commutator won't furnish. You actually have to go up to second order here to finish the job when you do for special component transformations. Okay? Because the first commutator will give some other operator here, won't give a k-mu back. Okay? And you want to write it in terms of k-mu on the left hand side. Okay? So for k-mu it's just it's the same thing, but you must go to second order to finish the job. Okay? You can understand here. For the scalings, we kept first order because the first order commutator gives you back the moment operator right on. And if you wanted to go to second order, you just keep reproducing the moment operator, so it doesn't matter. And the result for the k-mu at a point x is y delta x blue minus okay, this is the reason why, because I'm going to commute therapy as the spin part. Okay? So I have to commute them all over again. If you want to, I just suggest you do this computation and think of it as an exercise. Okay, and you see this is much more complicated, and for completeness, of course, the momentum operator acting at a field at a point x is just divided by mu. Okay, in fact, I use this in the other three above. Okay, so job done. We started with the representation for fields located at the origin, and we have translations. Here's an example for the scaling, that's the easiest. If you do this for F generator, for homo generator, there's this representation at any point x. And you can immediately see that if you select x equals 0, you just recover what you can put to that. Okay? And now here comes one important observation. Recall that when we discussed the conformal algebra, we noticed the presence of that ladder structure for scaling dimensions. Okay, we had mu raises the scaling dimension of states, and mu lowers the scaling dimension of states. And remember, we defined primary state as being those states are annihilated by the special conformal transformations. Okay, and here we can see the same thing but for fields. Okay, fields will have the same classification. We're going to have primary fields, and we're going to have standard fields, or you can also call them secondary fields. Okay, just primary operators, the primary fields are defined as those fields that are annihilated by mu, and the second fields are found by acting with mu on primaries. Okay. It is just, what everyone usually does with the ladder algebra. Okay? And by looking, especially here already, you can see a class of primary fields triggered. Any field inserted at the origin will be annihilated by the special conformal transformations. Okay, so we have a natural choice, a natural class, if you want, for primary fields in any set T. Okay, and again, these fields are anything. It could be scalar fields or spinor fields, vector fields, tensor fields, whatever you want. If the theory has conformal symmetry, if you put a field with the origin, whatever you call the origin, of course, then this field is going to be a primary. Okay.
Do you know how many primaries you have?
Usually for free theories you can have lots of primaries. When you have interacting field theories, the number of primaries usually pretty low, because you can think that the equation of motion kind of relates. If you have say if you have a this is just I forgot the word for it. Okay. This is not a rigorous explanation, but just give you the idea. If you take, say, a free scalar, okay, no mass because you want conformal symmetry, then usually you have that phi is a primary. Okay, you have that phi squared is a primary. And same thing for phi 3, phi 4, and so on. Okay, they are going to be primaries. One way to understand this is because what are the segment fields? We get a primary, we find a primary, say we found a primary. We act with the mu. Okay? But acting with the mu is just putting a derivative on the field. Okay? So usually one way to find to seek primaries instead of solving, if you're not at the origin, if any other point, you have to solve the differential equation. It's just it's a pain. Okay? One easier way to do is just you take your operator and you see if it can be written as a derivative of some other operator. Okay? If it cannot, then it is a primary. If it is written as a derivative of another operator, then it is a descendant. Okay? This is just a shortcut. Okay? And for free theory, phi turns out to be a primary. We have free scalar theory. Then phi squared, phi 3, phi 4. All of these powers cannot be written as derivatives of phi. Okay? But if you put, say, the back to the fourth interaction here, then the equation of motion is going to be like the inversion of phi equals lambda phi 3. Okay? So now we have some double inversion, which is two derivatives acting on a primary and give you phi 3. So phi 3 ceases to be a primary in an interacting theory. Okay? This is just, it's not rigorous at all, you have to be more careful with this kind of thing, but this gives you an idea. Usually on free theories, you have lots of primaries, but then again, free theories are not usually much interested at all. At least not by themselves. If they are embedded in some other theory, it might be. And but when you plug in interactions to a free theory, then usually you start some fields that were primary cease to be primary. Okay. If you want to be more rigorous, you have to look to the randomization group flow. Okay. You set an operator, then the flow will be an operator. They will be related by derivative. They're more rigorous way to do this. Okay? This was your question?
Yeah, no, it gave me an idea. Yeah.
Any more questions? So, what I was saying? Remember what I was saying? Okay, the message is this, okay? If you take any field, put it in the origin, any field, any operator, put it in the origin, it'll be, okay, that was what I was talking about. It's going to be a primary field. So you have a natural set of primaries. They are just fields or any operators at the origin. Okay? And of course, if your field is not in the origin, it can turn out to be a primary field as well, but you either solve this differential equation, okay, you say that pick this right hand side equals to 0 and try to solve. See if your field is a solution to the differential equation, or you can just do the much easier strategies and try to rewrite your field as a derivative of some other field. Okay, if you can do this, it is a descendant. If you cannot do this, it is probably a primary. Okay, and the point of radial quantization is to make this observation that any field or operator located at the origin, if one is a primary field or primary operator, and use this observation to quantize our theory in a different way that we do, say, in a point-ahead invariant theory, in some quantum field theory. And just to remind you, the standard quantization. Of course, I won't go into much details yet. Just remind you of the idea. So, yeah, this is for standard QFTs, okay, without a solution. You just you pick your spacetime and then you foliate it by equal time surfaces. Okay? Why? Because the Hamiltonian is the generator of. I'm sorry. You take your spacetime, you foliate it on an equal time surface. Say this is a t, then this is going to be t plus delta t. It's going to be t plus 2 delta t, and so on. Okay? And the operator, you have an evolution operator u that takes you from one equal time surface to another equal time surface, and it is just the Hamiltonian. Okay? This is the evolution operator, and what you do with your states, you have those in and out states. They live in these equal time surfaces. Each equal time surface is a Hilbert space. Okay? You assign a Hilbert space, when all Hilbert space in every slice, and since different slices are connected by a symmetry generator, the Hamiltonian, then this Hilbert space is actually the same, isomorphic if you want, so on. Okay? So that is what one has in mind usually when you do your standard quantization in the standard quantum field theories. So like equal time surfaces, each one has a Hilbert space and they are connected by the evolution operator that is built from the Hamiltonian generator, the time translations. And because of this, every Hilbert space is the same, and you label your states by momentum eigenstates. Okay, so you have a state with momentum k, you act with the mu, and we just produce this momentum k mu, the state. Okay. Now, because of this, again, remember that on CFTs, because of the structure of around the scaling operators, we chose to actually use the scaling operator to label our states. Okay, it's just more convenient because I have this other structure. And since the scaling operators do not commute with the Hamiltonian, we cannot do, but at least it wouldn't be wise to foliate our spacetime by equal time surfaces. Okay, what we're gonna do is this thing that we call radial quantization. Instead, we're going to foliate our spacetime. Let me just this radial quantization. What do you do with foliate spacetime? By equal radius surfaces, or hypersurface. Okay, so we choose one point to be the origin. Okay, it can be any point. I pick a point, call it the origin. Then I'm gonna foliate spacetime on equal radius spheres. Okay, and I'll play the same game. Each of those equal radius spheres is going to have a Hilbert space. Okay. So this here has a Hilbert space. And different surfaces are connected by an evolution operator. Say U. Which now is just scalings. Okay, so scalings will play the role of Hamiltonians in CFTs. Okay, and it is of the finite. The Hilbert space operator U is going to be EI the scaling generator, some delta, because there's some coordinate changes a little bit, but just see how I call them. Delta. I'll leave delta. Might be not the wisest choice to call it tall. But it also enforces the idea that for CFTs in radial quantization, it is the scaling operator, it is the Hamiltonian. And in fact, if you go to the literature, some more specialized, if you go outside from lecture notes and things like that, they will usually say, okay, the Hamiltonian D, they'll call the scaling energy, the scaling dimension, like the energy. Okay, they are just playing with this analogy. Okay, so make it clear. For a standard quantum field, we have equal time foliation of space-time. We have momentum eigenstates and different Hilbert spaces that each of these equal time circuits are connected by essentially the Hamiltonian operator that generates time translations. For a CFT, on the other hand, followed by equal radii surfaces. We label our states by scaling dimension eigenstates, we shall call delta. Okay. And as discussed, it's still here. Okay. As I discussed this, if this eigenstate, the eigenvalue is pre-measured. So this is going to be the eigenstates. In here, we're considering scalars for simplicity. Of course, if I have spinning fields, then we also have a mu, say delta S, where S is the spin, and this will furnish representation, a matrix that represents the commutator of gamma matrices for fermions and so on. Okay. But we're just going to focus on scalar field, scalar operators for simplicity. And the evolution operator is given by this. That is a tau. It is not time, of course, it is, you want this kind of radius here. Okay? And since we foliating our spacetime by these equal radius surface, this just begs for us to use spherical coordinates. Okay? And this will give a nice interpretation between radial quantization and the standard quantization. Okay. So our line element we're just going to write as dr squared plus r squared. Some volume element here. Okay. In a d-dimensional space. Okay? And we're going to employ we're using spherical coordinates. Now I'm going to make another coordinate change on the radius. I'm going to call this radius exponential of this tau, okay? The same tau here. And why do you do this? Okay? If you do this, then of course this line element becomes, we pick up an exponential here that factors out from here, from this differential, and we end up with Okay. Now this is just a conformal factor. Okay. I could do just a conformal transformation or a Radial transformation and just get rid of this guy. Okay. So. Is it? Here, just use the say a Radial transformation to eliminate this scaling factor. Okay. Because it doesn't matter. And what have we found here? We started with a metric for a sphere, say, S for sphere. We use this coordinates and then a Radial transformation. We are allowed to do this because again we have a conformal symmetry in our problem, and we end up with the metric of a cylinder. Okay, we have some angular coordinates here, and then we just have a line. Okay, so this basically R times S T. Okay, this is just a cylinder. So you can think that cylinders and spheres are equivalent by conformal transformation. Okay, as far as conformal transformations go. The reason this is cool or useful is because when we do standard quantization, we can just use the same. We can employ spherical coordinates for the spatial. Can use spherical coordinates for the spatial directions, and time will just be aligned. Okay, I'm using time evolution, slicing by equal time surfaces. So in standard quantization, we also have a cylinder. Okay, if you use the correct coordinates. Spherical coordinates for spatial part, and time just stays aligned. And this allows us to think or to map, say, in states and out states that we're familiar with from standard quantization to radial quantization. Because remember, in a standard quantum field theory, we start from in states that are inserted at time equals minus infinity, and then we evolve that this is involved, they interact, and we end up with some states in the far future at t going to plus infinity. Okay? And again, on standard quantum field theory, we have t going to minus infinity. We have what we call the in states. There are the states, again, you suppose that there are no interactions at the far past. So we can prepare on the lab some in states or they're involved. Then we measure whatever comes out in the far future. Okay? So these are the out states. And on radial quantization, it would seem we'd lose this picture because we're going to start from the origin, okay? We don't have say a far past or something like that. We might have some kind of far future. But if we employ this coordinate and do a Radial transformation, which again are allowed because we have conformal symmetry, then we can see that we have a cylinder here, okay? And where this tau here is playing the role of time here. So when I pick tau and go to minus infinity, this is, you're not too happy about this. Okay, then.
No, I still, but okay, somehow it looks, so it's a time evolution operator, it's just, I mean, so it somehow it looks boring, no? I mean, you're
With this?
Yeah, I mean.
Is what?
No, I mean, you're building your Hilbert space as eigenstates of an operator, like in quantum
Of the
theory.
scaling operator.
Normally it's interesting because the Hamiltonian is not, I mean, is not just a simple translation or whatever. So, but here, like the time evolution operator is already diagonalized by the.
Yeah, but that's why safeties are powerful.
Yeah, but then it looks like boring, no? I mean.
No, but here's the point. If you again, if you do free CFT, then it's gonna be a bit
But
more.
it looks not
usual.
always like a free theory. I mean, if you're in
No,
this
no, but
picture-
here's the point. The problem on interacting CFTs is that usually you do not know the eigenvalues. Okay, you have a framework
Okay.
where you know, okay, I can diagonalize. I know this guy is diagonalized, and so because of this, I label my states by this scaling eigenstates, and I have this ladder operator. I can just raise and lower. But the problem actually is for interacting field theory because of interaction, wave function normalization, and so on. You don't know what the actual eigenvalue is, and this is a big problem. Okay? Usually you have to.
Okay.
Okay, so just to finish the thought, in interacting CFT, you usually start by looking, trying to find all the primaries, and you say, okay, I found all my these are all my primaries. And again, as I are, they're usually like few, like 2 or 3 primaries typically, and then you have to you know the 2, 3, and 4-point functions up to all those remarks. I assume you know the function completely the 2-point functions, the 3-point functions you know up to the structure constants, and then from the 4-point functions forward, don't even know the functional form. And all these data, the structure constants and conformal blocks, they you need the dynamics. Okay, the theory. You need conformal symmetry plus dynamics to determine it. And this is what constitutes a problem of interactive CFT. In general, it's not trivial. Okay. If it is a free CFT, then typically your scaling dimension will just be the usual mass dimension of your field that you can read direct from the Lagrangian, and then just solve the theory. Okay. Any more questions? Okay. No? Okay. So just let's go back. Standard quantum field theory, we create instates by these instates are created by time equals minus infinity, and then we measure the outstates that live in time going to plus infinity. And here, again, when you do radial quantization, if we employ this coordinate change, again, we eliminate this scaling factor because we have a conformal symmetry, we can just do a conformal transformation and eliminate it. We end up with a cylinder. And we can play the same game. We can have instates, tau minus infinity, and outstates at tau going to plus infinity. And by this map, this just corresponds to r equals 0. Okay, tau minus infinity maps to the origin. Okay, and tau going to plus infinity maps to an infinite radius. So you can see that you do radial quantization. You just need to specify your primary operator, primary fields here at the origin, and we generate primary states. And then this evolution is just doing that. It's just taking your in states and evolving to the out states. Okay, it is basically the same. Okay. This is what the people call the, let's see here. This is what people call the cylinder interpretation, something like that. I mean, it helps us become more familiar with this picture of radial quantization. Okay, it is pretty much like working on standard quantum field theory, standard quantization, just that my Hamiltonian is not the Hamiltonian anymore, it's the scaling operating. My eigenvalues are not energy and momenta, it's just the scaling dimensions. Okay? But these are just names, okay? There's basically the exact same thing we do in quantum field theory. Okay? Any question about that? Nope. And let's see. Okay. Just the punchline here is instates in QFT, they correspond to primary states. In CFT, okay? By virtue of this map here. Okay. actually the operator state correspondence. I don't know if I'll get into that. There is maybe some details here that I'm missing. Okay, let me just, before I move up, okay, that is indeed one remark. Say it. It is about taking the conjugates. Okay. Conjugating in a radial quantization. Recall from the conformal algebra that we have this lattice section on the conformal algebra, and if we push for let's push the analogy with this ladder algebra, then we'd be inclined to say that P mu dagger is K mu, vice versa. Okay, because in another algebra, the raising and operators are conjugate to each other. Okay, and that conjugation just means Hermitian conjugation. Okay, just transpose and take the complex conjugate. Okay, in CFTs, in this radial quantizations framework, what we mean by we use the Hermitian conjugation symbol to denote that the point is it is a conjugation, but it is not Hermitian conjugation itself. Okay, and in CFTs the dagger symbol corresponds to inversion conjugation. I'm going to remind you why. We discussed, I guess, in the second lecture, at the beginning of the third lecture, that you can think of conformal transformations and conformity arrays and so on as inversion conjugated translation. Okay? Again, you pick a point, x mu, inverted, okay, like I, end up with this, then you apply a translation. So you get this. Now you invert again, and what you end up is just if you work out all the factors correctly, you end up with 1 plus 2, which is just a finite special conformal transformation that we discussed in the second lecture. Okay, and this is all motivated by this other algebra. Okay, in CFTs, in radial quantization, when you see the symbol of Hermitian conjugation, it is not Hermitian conjugation, it is just inversion conjugation. Okay? We can put this symbol in analogy with the usual ladder algebra of the harmonic oscillator and so on. But then you remind that mu is actually an inversion conjugation of translations. So you can see that the symbol in CFTs radial quantization means just inversion conjugation. Okay? So with this we can compute say the conjugate of rotations. Okay? The conjugate of rotations, if you do the same game here, pick a point, invert it, do a rotation in the inverse space, then invert back, you're going to see that you end up with the same rotation. Okay? If you do with dilatations, it's probably a minus here, I guess, or something like that. Okay. You have to work out what actually happens to the generator, but what it does happen is that you take scaling and this maps to the inverse scale. Okay, so if you dilate by lambda, then the conjugate just means that you're dilating by 1 over lambda. You're actually contracting. Okay, inverse scale. And of course, Ku is the conjugate in the inversion conjugate of mu, and vice versa. Mu is the inversion conjugate of Ku. Okay, and this is gonna play. This observation is gonna play some role in when we discuss maybe in the next lecture. We could do this now instead of going. No, we need the partition correspondence. Okay, this is going to play a role when we discuss the unitarity bounds next lecture. Okay, meaning again, as we discussed, the scaling operator is not the Hilbert space scaling operator is non-unitary, so this generator is not Hermitian. So you can again have problems with unitarity. So already anticipate in the second lecture that we will impose unitarity and see that this constrains the spectrum of the scaling dimensions. Okay, in that computation we're going to do next lecture. This observation of conjugates is going to play a role. Okay, I could do this here, but we need in order for you to understand completely what's going on, we need the operator state correspondence, and which maybe I leave it to the next lecture. Are there any questions about this? You can ask questions if you arrive late. Okay. No, because I'm going to end today. If there are no questions. No? That's it. Next lecture I'm gonna review all of this, maybe in some detail, because they are important ideas, so I'm just gonna hammer into your heads and for everyone that isn't present here today. And we're gonna go to this operator state correspondence and maybe compute this unitarity bounds. And then probably in the other lecture discuss the operator state correspondence. No, sorry, the operator product expansion, which is the actual computational tool on CFTs, and give some examples. Okay, this is actually lacking examples right now, but I hope you're not bothered by this. Okay, so see you next time. Perguntas, podem.